In this video, we're going to discuss a full example of fitting one of the hierarchical linear models we just discussed. Specifically, fitting one of the most complicated we just discussed, the random intercepts and slopes model. And we're going to actually add in a level 2 independent variable for fun. So I'm going to use the hypothetical data situation that we've been discussing all along. That is, we're going to look at a model of salary based on skill at the individual level. And then the company level, we're going to look at, as I mentioned earlier, random intercepts and slopes. But I'm also going to let public versus private companies impact the base pay. So public versus private isn't going to be something I assess at the slope level. It is going to be something I assess at the intercept level. I should note that public versus private at the intercept level isn't necessarily going to make the model predicting salary fit better, because the use of 0J allows the different companies to have their own intercepts already. However, I can test if that change in base pay is related to public versus private companies, and this lets me fit that in. Now, that's at a broad speaking level. That's a little bit technically untrue, but we won't go into the details. But again, at the broad level, if that's where you're at and you understand the fact that public isn't really going to help me predict salary better, because each company already gets um, their own base pay level, and so public doesn't actually improve that prediction, then you're on the right track. There's a couple of technical reasons why that may not be true, but that's definitely the right track. Now, it's important to be able to read this level 1 and level 2 model understand how this is, in fact, constructed and what this is saying. So reading through the beta 0 level 1, the salary equals beta 0j plus beta 1j skill plus epsilon sub ij tells me that I have an intercept and a slope, and I'm looking at least at the individual level, the relationship between an individual level skill and the individual level salary. The extra subscript sub j on here lets me know that there's a second level of information that I'm accounting for, and in our case, that's the company level information demonstrated in level 2. The beta sub 0j, and again, thinking about the context in terms of skill versus salary, that level 1 model, I can think of beta 0 as base pay. That is the pay when skill is equal to 0. So here, the base pay model is going to have a default level for all of the companies, and then it's going to have an adjustment for public versus private company, and then it's going to allow random adjustment so that each company can have their own. And again, that's the random intercepts component, letting all of the companies have a fully customized base pay structure. Similarly, with beta sub 1j, I can read through that model, the bottom model demonstrated here, the bottom equation. The gamma sub 1, 0 is the average over everybody, and then at the u sub 1j lets me have a fully customized skill compensation model for each one of the companies. So I'm seeing that that's the random slope component, and again, that introduces company by company slope that lets each company be different in the skill compensation program that it offers. All right, well, let's look at our results. In general, results come in two tables that we tend to look at. We look at the fixed parameter estimates and the covariance parameter estimates. In SPSS, they actually come out in reverse order, but we're going to interpret top down. So I changed them up here. And let's go on and jump in and interpret this covariance table first for the covariance parameter estimates. So UN11 is the variance of U sub 0j. So the variance of the first random components, which is our base pay, that intercept model. And I don't think I talk about it in the slides actually, but residual, that's the epsilon sub ij. So I have the epsilon sub ij, that's our error. And then I have the variance of the base pay among the companies. Now, when I look at this, I have my variance component that's in the EST column. So that would be variance of u sub ij is 0.6280. And if this were an intercepts only model, I could use that and the residual, the variance of epsilon, to put together an ICC. This is more complicated than that, so I wouldn't typically do that with this model. But what I can assess is the statistical significance of this. What I can see is that this is a statistically significant variance impactor. In fact, in the SPSS output, we take all of our significances and divide by 2 when we interpret them. That's a weird thing. So I take these significances and divide by 2 to interpret comparing these p-values to 0.05. So I have about a 0.2 p-value for UN11. That's the variance among companies in base pay, indicating that companies have a statistically significant variance in base pay after accounting for the other effects. Now, UN22 represents the variance in U sub 1j, that is the variance in skill compensation. So that's the second random effects component that we looked at in this model. We have 2 random components, U sub 0j for the base pay and U sub 1j, that is the company variability in skill compensation in that model. Interpreting that and again dividing the significance by 2, I see that skill compensation does statistically significantly vary from company to company after accounting for other effects. That is to say, it's important that we have both of these random components in the model because companies are varying based on this. Now you'll notice that there's a third unstructured variance component in this, and that's what the UN stands for, is unstructured. And that's the relationship between the company difference in base pay and the company difference in skill compensation. So thinking about this, I have the base pay being higher or lower and the skill compensation being higher or lower. And what we're saying is, as we maybe increase the base pay for company, does the skill compensation also increase or does it maybe decrease? Interpreting this, I can see that the estimate for UN21, the relationship or covariance between the adjustment to base pay at the company level and the adjustment to the skill compensation at the company level, is negative, and it's statistically significantly negative. That is, as one of those increases, the other decreases. And I will use the base pay as the one that increases, which means that as base pay increases, skill compensation statistically significantly tends to decrease. And you can think about that as kind of the pay curve flattening out. So if I hire you at a higher salary, according to this, on average, there is a statistically significant relationship that I'm going to compensate you less as your experience increases. So maybe I hit a salary cap or something like that. That could explain this effect. And I should mention this is all, some fun data, but it's not necessarily related to our outcome. I kind of repurposed this a little bit. Now, it is important to look at these random effects because specifically for the unstructured coefficient UN22, again, UN unstructured, 22 represents the U sub 1j. That's the skill compensation being different by different companies. And as we talked about, this particular one indicates potentially an interaction effect. And here in the covariance parameter estimates, we can see that this is a statistically significant interaction effect. So that's why this is important to account for first, is because it's important to acknowledge the interaction effects before we interpret the main effects. And we want to be careful about that. But now let's interpret these fixed effects. In this particular model, and again, it's important to realize this is not actually data on this particular situation, but skill is not related to salary after controlling for company. After controlling for what company you come from, Now that includes the public-private, so I don't necessarily need to add public-private on there, but I guess you could if you wanted to because we did additionally explicitly model that. But we wouldn't have to because again, if you controlled for company, you controlled for whether or not the company was public and private. And in this case, again, in our model, skill wasn't statistically significantly related to your salary. Now, it's important to mention when we say this that there was a statistically significant interaction between skill and the company. That is, that unstructured variance component 2, that random effect of company on skill compensation was significant. So different companies compensate skill differently. So we can't really say skill isn't related. And even if skill was statistically significant, it would potentially be inappropriate to say skill is broadly related. Maybe a better way to describe this is that skill may or may not be related depending on what company you work for. So the relationship between skill and salary depends on the company. Now, public is a level 2 variable, and what you'll find in the SPSS output is that level 1 and level 2 variables, if they are fixed, are included in the same table. So we'll see level 1 and level 2 variables right next to each other. Here we can see public companies is a statistically significant predictor. That is, public companies are statistically significantly higher salaries than private companies. And again, this is a statistically significant difference in that base pay for the public companies. All right. Well, this has been quite a bit. We have covered a lot within this, but there is a heck of a lot left. We really have just touched on a lot of what we can do in hierarchical linear modeling. A lot of extensions that you can do with this. We didn't talk about this, but you can absolutely implement third levels and fourth levels. We did actually, mention this earlier in this lecture set, but we didn't actually do an example with a third level model. Of course, the interpretations become more complex. But you can absolutely do third and fourth and fifth level models if your data support that and that nesting structure makes sense. You can also do models over time with, again, time is your level 1 variable. But this is something that's very, very common. And again, gosh, with HLM, I feel like with all of our analyses, I've said there's a lot more we can do. But man, HLM is so true, so true. And this is a big one because HLM is I don't want to say most often, but it is very common to use time in HLM. Not always, and not even most of the time, but it's a common thing to see, and something that if you wanted to look at into HLM further, I think that would be a great additional thing to check out. One of the first things to check out. You can also use non-normal models. So we just talked about regular regression in the context of HLM, but you could absolutely do a logistic regression HLM. I will warn you, the interpretations become complex. They become very complex. And so it's important to realize that, just as HLM interpretations are more complex than regression, logistic regression interpretations are more complex than normal regression. And a logistic HLM interpretation is massively complex. So it is something to be aware of. We didn't get the chance to really focus on centering. We talked about kind of grand mean centering, which means centering around the average of the variable. But sometimes maybe we want to center around the company mean. So that is, I don't want to look at how a person's skill is related to salary for skill for everybody. I want to see if your skill is higher within that company. How is that related? And that can provide some different interpretations. We can also look at like how companies maybe have a level 2 effects on that variable. That is, what if companies have different skill levels? How does the company average skill level play out? And again, these are some advanced concepts of centering that we didn't discuss. And for your assignments, you'll just use the grand mean centering very likely. So that is an extension. That's not a main part of our lecture today. We didn't discuss sample size calculations. Sometimes you'll hear the 30-30 rule. That is 30 level 2 groups, in our case companies, each with 30 employees each, or 30 level 1 units within each of the 30 level 2 units. So that's a rule you'll hear sometimes. There's a lot more complex calculations in that. Some students think sometimes that 30 employees within each company sounds like a lot, 900 in your total sample. But consider this: in a regression model, how many participants do you think you need to run a simple linear regression? And maybe 50 or 60 participants to run a simple linear regression. But recall, if we do the random intercepts and slopes, what we are letting happen is every company gets their own regression model. So it makes sense that each company should have a sufficient sample size to be able to estimate that regression model. And so if you think 50 participants are necessary to do a regression model, well, gosh, maybe you need 50 participants from each company if you're going to do a random intercepts and slopes model. Of course, limiting just to have random intercepts instead of random intercepts and slopes can help your models to be a little bit more efficient in terms of sample size and lower sample size requirements. So there's a lot to consider within this, and it's something that is an extension you're welcome to check out. We didn't really discuss much of model fit statistics. We did talk about ICC, but there's a whole broad theory of different model fit statistics and testing for the overall general model fit. Incidentally, we talked about random versus fixed effects in our review, but we didn't discuss how we can really look at a variable and tell, should this be a fixed effect? Should this be a random effect? And there's some theories on what we do with high levels in a potential nesting structure. Sometimes might make more sense to consider them fixed than random in certain situations. Meta-analysis is actually a really, really important analytic technique, and it is its own standalone subfield aside from HLM. So don't hear this as saying HLM, meta-analysis is a strict subfield of HLM. I wouldn't consider that to be true, though there might be, at a technical level, some truth to that. But meta-analysis is really a standalone subfield that looks at combining a whole bunch of different studies together. So we take data from one study and data from a second, data from a third, and combine them all together with each of the participants nested within the study that I took them from. And so in that manner, meta-analysis can be looked at as a hierarchical type analysis, and it's actually a very important type of analysis. Some of the strongest data and evidence you can provide are data and evidence supported by meta-analysis. So it's an extremely important field, but maybe not strictly an HLM thing. And last but not least, maximum likelihood versus restricted maximum likelihood. We did not discuss. This is something involving the model fit and a technical detail that we skimmed over. Long story short, restricted maximum likelihood tends to perform a bit better when we have less level 2 groups. So if we have less companies, restricted maximum likelihood tends to work well, but it limits some of the statistics that we can calculate. Maximum likelihood has some other statistical options available with it. So I would probably default to restricted maximum likelihood, REML, and then if there's an chance where, or if there's an situation where I know I have a large sample size at level 2, I've got lots of companies in my sample, that maximum likelihood would work well, and I'm interested in one of the additional statistics that a maximum likelihood fit would provide me, then I might move to the maximum likelihood fit in that particular case. And that is the end of our hierarchical linear modeling lecture set. So check out our software video where we demonstrate how to implement HLM in software.